All right. Hi, thanks for coming. Hope you guys are having fun at Derbycon so far. This is my first time here, and in Louisville, actually. I'm not sure what I was expecting, but it's huge. This is actually only like one of my third or fourth conferences I've ever been to. And so I'm Alfredo. I'm going to talk to you a little bit about Android in-app purchases or in-app billing. I will use the terms interchangeably because even though we all call it IAP, Google thought it would be cool to call their API IAB because, you know, security by obscurity. So I'm a consultant and researcher at VSR in Boston. We mostly do a lot of, AppSec. We do the regular like network security stuff, and then we get to do a fair bit of mobile work in different areas. And so personally, I got interested in in-app billing or in-app purchasing a couple years ago. I was in New York City. I was sitting on the subway, and there was some kid playing Candy Crush, and I'd heard that this game was like super popular, and he's playing and he runs out of lives, and I'm like, well, that's kind of stupid, and so he has to buy more with actual money, and I'm like, well, that seems kind of dumb to me that you need to just pay to continue playing this game. And so I was wondering, can you bypass that? Can you just fake buying this stuff, or fake buy like these lollipop hammers and all of these buffs, and just cheat your way out of having to pay? It turns out that you can, and I could. But as it turns out, that once you strip out all of the IAP stuff from something like Candy Crush, it's really just a pretty mediocre match 3 game. So kind of the fun part is really breaking it, because playing it, not really worth it. So why even bother talking about in-app billing? Why is this an interesting topic, and why is it relevant? Well, most of all because of money. As with most things. That's the reason why most of our customers are in finance or healthcare or that sort of stuff, is because there's a lot of money there. Well, it turns out there's a lot of money in in-app purchases, and it is skyrocketing. In 2011, in-app purchase revenue hit $2 billion. It's supposed to hit about 14 this year, and it's projected to just keep on going. And as of right now, in-app purchases make up about 75% of revenue for mobile developers. So this is actually really big business, and it's just getting bigger, because for some reason, people are more than happy to drop 99 cents here and there to play their little time waster games on the subway or on the toilet or whatever, wherever it is people play Angry Birds and that sort of stuff. Now, I mention games because most top-grossing Android applications are games for some reason. There are exceptions. Pandora, for example, HBO Now, Tinder, I guess Snapchat just added in-app purchases, so you can add lensing effects to your snaps for $3 or whatever. But the vast majority are games. And so, I say that a lot of times. People are like, oh, well, games, that's not really a big deal. Who cares? People are cheating at video games. Well, it turns out there's actually a lot of money there. Supercell, who are the people that make Clash of Clans, saw their revenue triple between 2013 and 2014 to 1.7 billion US dollars. King, the guys who make Candy Crush, who are the top dogs right now, but are kind of on the downslope because they've been riding the Candy Crush wave for like 5 years at this point. They make about $2.4 billion a year. And this is almost exclusively through in-app purchases. So we're talking about video games having a lot of money in them. Outside of that, we're seeing the rise of stuff like mobile MMORPGs, massively multiplayer online role-playing games, though I'm sure most of you guys know what that is. There's, for example, a game that's very popular on iOS and Android called Clash of Order and Chaos Online, which is a traditional type MMO like World of Warcraft, but it's on mobile. And so we're starting to see the same kinds of gray markets where people are selling these virtual items or selling their accounts. They'll start an account, they'll grind it up to whatever the max level is and get some sweet items, and then they sell these accounts for $100, $200 a pop. So what that says is that if you're able to actually just cheat the system entirely, you're basically manufacturing money at a much smaller time cost than you would otherwise by having to legitimately get this stuff in the game. And essentially, if there's a lot of money to be made or had, you're going to attract bad actors. People who are going to figure out how to exploit the system and make their own gains without having to play by the rules. And as it happens, that is what happens, and we're going to talk a little bit about that, how you do that, and how you fix it, and how you prevent it. So, before we do that, let's talk a little bit about what Android in-app billing actually is. So in-app billing in general is just a way for people to buy things from developers without having to leave the application. This is an important distinction because stuff like Ticketmaster or Live Nation, they let you buy tickets from your phone, but you're ultimately just doing it through their standard APIs. You're giving them your payment data. You're going through the same way that a web user would. You're just doing it on your mobile device. In-app billing, the whole idea is you're doing it from the app itself. And Google's in-app billing API, the whole point is that you can make a purchase, a user can make a purchase without ever having to give you their payment data. So the way it works is the user says, hey, I want to purchase this thing. So then the app says, hey, Google Play, my user would like to purchase this SKU, this lollipop hammer. So then Google Play takes control and says, hey, give me your payment details. Do you actually want to buy this thing? The user says yes or no, whatever. And then Google says, okay, the payment went through, the purchase is complete. You can give them their content now. And the whole thing is, people like Supercell, King, all of these companies, they don't have to actually keep track of your credit card data. They don't have to take any kind of payment details, and that vastly simplifies the entire process, especially for users, because if you've ever bought something from an application, you click a button, you click a second button, and you've bought it. So it's very easy, and it makes it very simple for people to drop cash on stuff that they wouldn't otherwise. So this is an API provided by Google that allows you to interface with their Google Play Store, and they provide excellent documentation, like this extremely simple diagram. Unfortunately, this diagram is overly simplified and doesn't give you a good picture. So you have something like this. So this is what in-app billing actually looks like. My point here is that it is confusing. At its core, in-app billing relies on an inter-process communication mechanism that's part of Android called intents. So when you click on a button to buy something within an app, the app sends an intent to the Google Play app, which every Android phone has, and says, this user would like to buy this SKU. And then you interact with the Google Play app, you do your thing, and then the Google Play app sends an intent back to the app, to the original application, saying this is what happened. And so intents are just bundled data. You can just think of them as JSON really, because they effectively are serialized in a very similar way. Where you have okay, this was the SKU, this was the result of the transaction, and there's additional metadata. For example, when you say, "Hey, I'd like to buy this thing," this user would like to buy this thing, you send Google Play your public key, and that's what they use as your identifier. That's how they link up your request to who's actually getting paid, and they also use this because you have your private key registered on your Google Developer Console. It's kind of a weird scheme. So basically, your private key is private in the sense that only you and Google know it, and Google uses it to encrypt a signature for every purchase. So this "here is your purchase result" includes this signature that says this is how you can verify the authenticity of this transaction. But ultimately, implementing in-app billing is confusing, and because of that, developers take shortcuts or make mistakes that lead to exploitable vulnerabilities, and that's what we're going to look at here, because they essentially allow bad people, like us, to completely circumvent the process and get stuff for free. Google tries to make things simpler by providing you with a sample application that demonstrates how in-app billing works. It's like this fake little game where you can buy gas for your truck to make it go further. And so, it just kind of walks you through registering an SKU on your developer console and, what it would look like to send the right intents to buy a thing and so on and so forth. And they put a disclaimer. Hey, don't use this. This is not, production code. Make sure you modify it because it's missing, all kinds of other security precautions that we think you should take. So you probably shouldn't use this in your code. And as part of it, the core of it is this helper class called the IAB Helper that implements the in-app billing API. Now this class, like I said, is very streamlined because the whole point is it's a demo to walk you through this is what an intent for purchasing looks like, this is what our response will look like. Please don't use it. It's not for production. So what happens? Well, everybody uses it in production. Candy Crush literally just takes the class and copy pastes it. You have one of the other top grossing game, Marvel Battles, just takes it and copy pastes it. There's tons of other games where it's actually trivial to obfuscate in Android just by enabling ProGuard when you compile. So you'll just have class B, which is IAB Helper, and wholesale, and they haven't changed anything. And so they've looked at a lot of these templates on how these functions work, and left out critical things like how signature verification works, or sending in a security token with your purchase request so that you can verify authenticity. We'll talk about it in a minute. So this shouldn't be a surprise, but there are essentially cracked binaries for just about any major game that you can think of. Whether in the form of cracked APKs, or there are these fun little things called like Freedom and Lucky Patcher that you can put on a rooted Android device that essentially replace the entire Google Play API with a fake one, so that apps always think that you're buying from Google, but really you're just not doing anything at all. This is a problem in two ways. Obviously, it's a problem for developers in lost revenue. If you think about something like, so estimates I've seen that claim to be good, and these guys do market analysis. The idea is that Clash of Clans makes like $1 million a day. So like this is, which is crazy to me because things cost what, like $1 on there. So tons of people are dropping money on here. So the fact that you can cheat around this is literally lost revenue. But more importantly to me, really, I'm not go Supercell, but I think a bigger issue is that people downloading cracked binaries is a pretty big source of mobile malware, especially on Android. When they do surveys, they find that most people who have malware, it's because they downloaded something from an untrusted source. Or you have these things like Freedom and Lucky Patcher, which replace the Google Play API entirely, and those require you to then first root your phone and then download this, kind of intentionally shady code to run on your device, which is fine if we're doing it. But if it's just the guy who just wants to get stuff for free, he might also be downloading additional add-ons with his stuff that will take over his device, and that's kind of bad. So let's take a look then at how IAB is actually implemented and how we're going to exploit it. Are there any questions so far? I recognize that I'm talking a little fast, but feel free to interrupt me at any point. Yeah, feel free to interrupt me at any point. I can regain my train of thought if you have any questions, because I know before I started looking at this deeply, I didn't really know anything about in-app purchases or how they work. And I'm kind of taking for granted that you know certain things about Android itself. Yep. Yeah, and that's kind of what one of the things we're gonna talk about, and that's actually exactly what we're gonna do is we're gonna manipulate some intents, because ultimately, since all of this communication is happening inside the device, it's fairly trivial to man in the middle it. So in order to actually exploit this stuff, what we're going to use, or what I'm going to use, is something called Cydia Substrate. Who here is familiar with Cydia Substrate? Okay, right. Cool, so the back of the room knows about it. So Cydia Substrate is awesome. It came out in May of 2013. It was kind of an offshoot of Mobile Substrate, which was for iOS, made by this dude called Sorik, or Jay Freeman. And actually, I learned how to use this framework mostly by being on IRC with him and be like, this doesn't work. I don't know how to do this. Teach me, because your API is hard to use. And he did, because he's awesome. And Cydia Substrate, essentially what it is, it's a framework that allows you to modify the way an app behaves at runtime. So we know, hopefully, that Android is mostly Java. It's a Linux kernel, but most of the layer that we're going to interface with is Java. But instead of running a Java virtual machine, a stack-based Java virtual machine, we're running a register-based Dalvik virtual machine, which is essentially the same thing for our purposes. But one of the ways that they overcame things like shared libraries and slow loading is that when you first start your phone, when Android is booting up, it creates a prototypical virtual or DVM called the Zygote. And so all of your shared libraries and everything are loaded into the Zygote, and then when a new process spawns, it clones this virtual machine. So if you can modify the Zygote, that's going to propagate to all of your child processes. And that's essentially what Substrate does, is stuff is loaded from an app's classes.dex file, and you at runtime are going to inject your own definitions for classes and methods so you can do what you want. The way this works is pretty simple. You hook a class with a method that's part of their API, and what that does is that you're essentially, as soon as the class is loaded, you're hooking into it. And once that happens, you can pick a method or any number of methods, and you can modify them in really any way you can think of. You can change the way what they return. You can change their arguments, really anything, or you can use it for logging. We're using this to bypass in-app billing, but in my own work, Substrate is really useful for just any type of mobile engagement. As certificate pinning becomes more common, Substrate is great because you can modify the way that trust stores work and just say, hey, we're going to allow everything, so don't worry about pinning, and that way you can proxy your stuff through Burk like normal without even having to load a cert into your device. Or you can use Substrate to log, crypto functions. So you can see how it is that an app, anytime an application's invoking any kind of crypto, you can look through that very simply and see, okay, this is what they're doing. They're using, bad crypto here, or they're doing something questionable here, and I can look into that further. At one point, it actually built a dynamic vulnerability scanner that just basically runs on top of your application using Substrate, and it was rules based, and so you just kind of say, hey, look for this, things that fit into this template, like, use of MD5, or look for, write calls to the SD card. And so you just use the application, and this thing, would give you a report to say, this is the stuff that's happening in this application. And so it knocked out a lot of the automated stuff, and then you can manually go in and look further. So Substrate's really awesome. If you do any kind of mobile work, whether it's on mobile or on iOS or Android, it is invaluable, and I definitely recommend you check it out. But we're mostly going to use it to break this. And so our exploit example is going to focus on Candy Crush. I picked Candy Crush because it's been around for a really long time as a top-grossing app. It's, I think, number 2 or 3 today. It was number 1, 3 years ago, and it just seems like people don't get tired of it. It's also an app that commits a lot of the common errors that we're going to see in implementation of in-app billing. It's not unique in this respect. Where I could think of it, I've included examples from other applications, so you don't think I'm just picking on Candy Crush, or that that my methods here are one use only. The real problem here that we're addressing is the fact that almost all devs are doing things in the same way, and those ways are wrong, and so we need to fix that. So we're just going to kind of go through some of these common flaws, and then we're going to see how we're going to exploit those in a little bit. There is a lot of code, so I've tried to make that simple to look at, but let me know if it's not. So when you launch your purchase flow, one of the things that you can do is you can send in a token. This is just like it's like a hidden parameter on a form. It's a CSRF token essentially. And so the idea is that you send this to Google, this token, and then that way you get the token back, and that way you're able to match up a request with a result, so that for example, you don't have to worry about replay attacks or purchase request forgeries and stuff like that. Unsurprisingly, the Google's Helper class doesn't include that, because that's just making things more complicated, and so developers in production don't include that, and you just have like this empty string that they're sending through, and they're not even it's a simple thing to include or check, and they're not bothering because that's not what the sample did, which makes it a lot easier for us because it means we don't have to worry about forging that. Not really a vulnerability per se, but this is extremely common in just about every, I'm including like Candy Crush and Pandora here, but they do like step-by-step debugging in the logs. It's pretty trivial if you hook up an Android device to your computer and then run logcat, you can see it, whatever the device is logging. And as it turns out, people log a lot, especially for in-app billing. A lot of the default helper classes include a lot of log statements, and then also I suspect they do it because they need it to troubleshoot, and then they just leave it in. So it's really simple. If you're writing an exploit for an application, if it's not working, they're essentially doing step-by-step debugging for you, and you can see where things are breaking down. And that's really useful. It's not a vulnerability per se, but excessive logging is definitely a problem. And then one of the really big ones that just about everybody does, I have examples here from Candy Crush, from Pandora, from Clash of Clans, and it's essentially that signature verification. Like I said, when you send in a purchase request, Google does the thing with the user, and then it sends back the result to the application with a signature. Well, these signatures are verified typically by a Boolean function on the device. So it's entirely client-based. Developers haven't learned to think of the idea of the device itself as an untrusted client. And so if you're doing all of your signature verification locally, I can just always make it say that it verified. And that's one of the bigger problems. Client-side signature verification is a huge issue, just because, anyone who works in the web app world, I think, knows this, right? If you're doing all of your validation in JavaScript, people are just going to bypass that. And it's the same thing here. You need to be doing server-side checks if you actually care about your signatures. So I'm going to show you a quick demo. This is So essentially here, what we've done is we've rigged up Candy Crush so that we can buy things. Well, first I have to use my lollipop hammers because I can't buy more until I've used them all up. So I'm going to do that. But essentially what we've done is we've made it so that when I start the purchasing flow, if I cancel out of it instead of going through with it, the application gets okay, everything's good, he bought the thing, give him the stuff now, and it accepts that. So you click to go buy, you get now it's Google Play's ball, and you hit cancel, and it works. You never had to actually buy anything, and so you've completely bypassed the in-app purchasing. So how does this actually work? Well, it's actually really simple. It's like it's a very simple three-step process in order to just go in, modify a couple lines of code, and you've now completely broken this app. That's this is really the most important part of the app. If all of their revenue is from in-app purchases, they should probably do a better job of not letting you break that. So this looks very similar to what I showed you earlier. The first thing you're going to do is you're just going to hook their IAB Helper class because they're using the exact Google class, the Helper class. And then what you do is that you're going to replace the intent that Google sends back. So normally, if you cancel a transaction, Google says, "Oh, the user canceled. Never mind," and the app goes, "All right, well, I'm not giving you your thing then, obviously." And so what we're doing is, as the gentleman mentioned, is that since it's all done with intents, you can just replace the intent. And so what we do here is we just manufacture a successful transaction. Response code 0 means, hey, that worked. He bought the thing. The product ID is, the thing you bought, whether it's lollipop hammers or extra lives or what have you. And then everything else we just fake, because it doesn't matter. They don't check the order ID. We're going to put a fake signature in here. We're going to put a fake token because none of these things actually matter. Because the last thing we're doing is we're actually going to go into their security class and we're going to look at their verify signature methods, and we're just going to always make them return true. Because if you put something inside the client, I'm just going to bypass it. I say this a lot because it's kind of like one of the bigger takeaways is client-side trust is bad. And we know this, I thought. But as it turns out that when we move from one platform to another, we forget everything we learned in the last platform, and we start doing things over again.
Where would you put it instead?
What's that?
Where would you put it instead?
On the server.
Because you just replace the intent of your phone when you check out the server and just replace that?
No, because, well, I mean, I'm actually going to go into this in a little bit, but the idea then would be that you send the entire thing to the server, right? And the server performs signature verification on their end, and if it doesn't verify, it doesn't send you the content, right? Obviously, if you just had the server say, oh, all clear, then you could replace that as well. But the idea is then you'd have to put content on to the server side, and that actually is a valid strategy in a lot of cases for some of the context we're going to talk about. Yeah, there's no need to show the demo again. But this was trivial to break, and the API has gotten a little better because Google's kind of realized that developers are not doing server-side checks that they should be doing, and so they're kind of recognizing like, oh, we should probably, make things a little more robust on our end to make up for the developers not doing what they're supposed to do. But even so, I mean, they can't do it all. So it's a little harder to break now than it was 2 years ago, but it's still fairly easily breakable. And so there are some best practices that Google suggests and that we'll suggest that people should be following. And these are the kinds of things that you can suggest if you're pen testing an app that uses IAB Billing and isn't doing it properly. So kind of going back to your question, ultimately, the real big issue is client-side trust. We're doing everything on the client. We're verifying content, all of the signatures, all of the content is on the client itself, typically. So, for example, if you have, like something like Candy Crush, right? The lollipop hammers are not a real thing. They're just a counter that's maintained internally on the application, which is fine. Because that's a single-player, offline game. If people are cheating that, you're losing some money, but it's not really a big deal. But when you start talking about things like Clash of Clans or a lot of these online MMOs, now you're creating competitive environments where players are actually working against or together, or against each other or together, and so cheating now has greater repercussions because nobody wants to play in a hacked game. I mean, if you've ever played like I guess Call of Duty. And you log onto like a hacked map, like that's actually not fun, and people will stop playing if it becomes rampant. And in these cases where you already have an online infrastructure because you have an online game, it actually makes sense to put some of this stuff on the server where possible. So for example, you should instead have the client starts the purchase flow, you talk to Google, you get back, and then you send that off to the server. And the server decides the validity of these transactions based on data that only they have and that obviously the client can't manipulate, and then delivers the actual content. Like Pandora, right? So all of the music is actually streamed from their servers. It's not obviously it's not all on the client, but that's irrelevant if the client is the one that says, "Hey, you should stream me this content." And you shouldn't give me any ads because I bought this thing. I bought Pandora 1. Trust me, I bought Pandora 1. And the server says, okay, here's all the music. You don't get any ads. What should be happening is, you have to buy it via the app, send that stuff to the server, and then the server says, okay, this was a valid purchase. I'm going to mark your account on the server as one that does not get ads. But that's not what they do. So obviously, you're able to circumvent that. It kind of going back to a game context, it will often make sense for servers to keep track of data rather than letting the client do it. I mean, this isn't like, rocket science, because this is true in the web world, this is true in the desktop world, Instead of having a client say, these are the things that I have, this is my hit point value, this is my magic point value, here you go, server, this is what I am, the server should be the client should be querying the server who should have these values so that they can't be manipulated. I mean, this is essentially a solved problem in the PC world, and the mobile world has a lot that they could learn from that. There are, of course, exceptions. I mean, there's like a major online game that launched like a year ago And people very quickly found out just by running, just from PCAP files that hit point values were stored client-side and money values were stored client-side, and they were just sent as network packets. So they're like, okay, well, we're just going to always tell the server that we have all the stuff. And so you had people running around this, massively multiplayer game with infinite health and infinite money, and that created a pretty big backlash for the game. I mean, they actually just recently did major server consolidation because their player bases dropped dramatically. And so I guess my point here is that the cheating in games doesn't sound serious, but it definitely results in lost revenue for the actual developers in a very meaningful way. And so that's why we need to care about this and why we need to help our clients do things better. So another thing that you can do, just going back to one of the first issues I talked about, is add a CSRF token to your transactions. It'll protect your customers from request forgeries or replay attacks. This isn't anything new to anyone who's in the web app world, and it shouldn't be new to people in the mobile world either. Something that I see all too frequently is completely unobfuscated binaries. And I know a lot of people think obfuscation is useless. I don't think it's useless. I don't think it's a solution per se, because ultimately, if I care enough, I'm going to, follow all of these, this logic flow of these functions and find the things I'm really looking for. But obfuscation definitely helps, and it's trivial to do in Android. I mean, literally, when you're compiling, you check a box to enable ProGuard, and your application is mostly obfuscated, and it's a pain to work with. I mean, some of these applications that I look at are obfuscated, and but most aren't. And that makes it a lot easier to work with, to figure out, where the stuff that I need to break is, and actually break them. And if it's that easy to do, to actually obfuscate, I don't see why you're not doing it. At the very least, it can convince an attacker to pick, lower hanging fruit than your own application. And there are other, solutions that people swear are fail-safes, like ArcSand's all about their magical obfuscation. But it's just kind of a simple thing to do that'll at least help. I mentioned that your public key is the way that Google identifies you and actually, handles the purchase flow, right? So basically, you say, hey, my customer would like to purchase item A. This is my public key. They look up your public key. They're like, oh, this is developer blah. This guy bought this thing, and we're going to put this money in their account. So whether or not you think this is a flawed process, which you could certainly argue effectively, it's the way it is. And so Google says, hey, obfuscate your public key, because that's the thing that we do now. Because if you don't, someone can take your binary, take your public key out, put theirs in, recompile, distribute, and now anytime somebody buys a thing, they're getting your money. And so that sucks. I mean, there's really no two ways about it. I mean, that's poor design, but it is what developers have to work with. So if you do want to get your money, you should kind of try to make sure that your public key is less exposed than it could be, so that people can't easily replace it and get your money. And then here's really the real big one, which is don't use unmodified code that you downloaded off the internet. I see this a lot these days, especially in mobile. But where I'll see some interesting comment like "don't use this," and then I'll copy paste this little swath of code, and it turns out it came from a GitHub repo of this guy just kind of showing a proof of concept of how to implement RSA in Android. And he's like, this is my school project. He's like, don't use this. And then you see that in a production banking app, and you're like, why? How did this happen? And people don't. I mean, it's just that's the really critical one, because if I understand that it's hard sometimes to implement certain functionality, but you can't just download something that you haven't vetted and use that. I mean, I think stuff like Heartbleed has already shown us that even well-established libraries and programs, like stuff like Bash and OpenSSL, have these long-standing vulnerabilities that people haven't actually combed through and found. So if these things are problematic, I mean, free code that you just get off of GitHub or Stack Overflow are even bigger issues, and we need to make sure that we're not just downloading that stuff and putting in unvetted malicious code into our applications. And I mean, because I remember when I was first looking through this stuff, most Android apps were either using this IAB Helper that they literally copy pasted from Google, or there was a Stack Overflow question that was like, I'm having trouble implementing InApp Billing in my application. Can you help me here? And somebody was like, oh, here's an example, and then you'd find that example Stack Overflow answer in tons of these top grossing apps. And going back to earlier, these guys have a lot of money and development, or should have a lot of, they do have a lot of money, so they should have a lot of development resources, and they could be doing things better. And so ultimately, our job as pen testers is to learn to recognize, these sorts of issues. When we're testing mobile applications that have in-app purchases, there's things you can look for to see if they're doing it right or if they're doing it wrong. And then hopefully we can implement that. We can use that knowledge to actually tell our customers what they need to be doing better. And that's essentially it. That as security professionals, that's our job. We can help developers do things right. We can help them spot the mistakes and actually implement this stuff properly. It's definitely doable. There are good cases. Off the top of my head, there's Comixology, which sells comic books, digital comic books, and they have an Android application that uses in-app purchases, and they do all the things right. I mean, they keep all of their content on the server side, like they should, and they do all of their checks and stuff on the server side, and so you can't actually get free comics, which sucks for me, but at least they're doing things properly. I definitely spoke very quickly, and so I'm effectively finished. So I'll be happy to take questions. Yeah.
Is it possible where you can profile and detect Cydia bugs?
Not really, not directly. No. I mean, because if you did, I would just rewrite your code so that you don't. It's the same sort of way root detection is pointless, because to run Cydia, for example, you need to have root, right? And so so that kind of breaks that. There are certain things that people try to claim, like Arxan definitely claims that they can work around some of that stuff, but I haven't actually seen data that really supports it, where they can actually detect Cydia at runtime. It's ultimately a flaw of the architecture of Android, and I don't really know that there's anything you can do about that, in the same way that you can't control the way your JavaScript is going to be executed on a client browser. And so the only real solution is, accept that the client can't be trusted, and what do we do now?
What does iOS do differently, and this question may be rhetorical, but and why hasn't that motivated people to say, oh, maybe we should,
Oh, no, the way that iOS implements in-app purchases is completely different, but also breakable. But because it's just a completely different platform, so that's why I just covered one. But there are cracked binaries for iOS apps. It's a lot of the similar kinds of stuff that you would see on Android, and it's harder because while runtime code injection is something you can do on iOS too, it's a little harder than it is on Android. But you could do the same kind of thing with mobile Substrate, which is the iOS version. Because ultimately, this whole idea of client-side trust is just very weak in mobile from what I have seen. Where we've learned a lot of this stuff from the web, but you look at, a lot of, we were just looking at a banking app the other day, and they have a PIN protection, right? And it's literally just a function that you can hook and say, oh, never mind, PIN's good. And that's to protect your money. So for some reason, a lot of these lessons from the web haven't translated to Android and iOS. Yeah.
and moving a lot of functionality to servers is going to incur a lot of infrastructure costs and building and maintaining servers. Do you think that the loss strategy would outweigh that?
No, honestly, for someone like Candy Crush, probably not. I mean, especially as entrenched as they are at this point and this far into their life cycle. But most popular games now are online. I mean, if you look at the top, 100 that I showed you at the beginning, like they're almost all online games. A lot of them are competitive, so they actually already have some kind of server infrastructure that they could be leveraging, but aren't. And most of what we're talking about here isn't going to incur a huge additional load on the system. Yeah.
Have you talked to Google about changing their sample code?
No, I have not talked to Google about changing their sample code. I mean, so here's the thing: like, their sample code has a big disclaimer that says we don't include this stuff.
The words on the screen don't really.
Yeah, I mean, they literally say, hey, we don't include the security token because that would just make this whole already confusing process. I mean, you can tell from the way they write things that they understand that their API is really hard to use. And so they've really stripped down their examples so that they're easy to use. But then, you've stripped out a lot of the security. And so they're aware of that, and I guess they just kind of cover their bases by, by saying, hey, don't use this. But also, the API has evolved. Like in the last year or so, they've added some extra checks that Google does on their end. But ultimately, those checks get sent back to the client, and then that can be manipulated at that point. So I mean, they're trying, but there's only so much they can do because they don't hold your content, and that's really the key.
Can you do that? Can you do this manipulating the intents without the mobile substrate?
Yes, absolutely. On a non-rooted device. So here's the thing. If you wanted to do some of this stuff on a non-rooted device, you could download a cracked binary that does things differently. So, like a cracked Clash of Clans or a cracked, like, for example, you can do on a non-rooted device, you can run a Windows desktop application that'll talk to your Clash of Clans and, like, set your energy crystals or whatever their IAP currency is to whatever you want. On a large scale, you cannot manipulate intents from another process unless you have root. That's one of the protections of that's exactly what the mechanism is supposed to protect you against, right? Is that another process is not going to mess with your memory and your data. It's just that once you have root, that all goes out the window.
So for general users, it's a little bit less of a threat because they don't have a rooted device.
Yeah, well, what a general user would do is just download a modified version of the application, which doesn't require root, because then you've modified the application itself.
But another malicious application will not be able to manipulate the intents.
No, but I guess what I'm saying is you wouldn't have to at that point, because what I did was I modified the behavior of Candy Crush, right? At runtime, I could have also just decompiled the code, modified it, and recompiled, which is what these cracked binaries do. And so then you don't have to worry about having root at that point.
I guess it was coming from a component, from a configuration, like somebody can use the manipulating intents to steal from money. Right?
No.
They still charge you and they get pieces of the money in their account. Not in the Candy Crush account.
No one should be. That's the whole point of the mechanism is intents can't be manipulated by different processes. Alrighty. Any other questions? If not, I think we're good to go. All right. Well, thank you very much. If you have any other questions, or if you happen across any interesting IAB issues and you'd feel like chatting about it, shoot me an email. I'd be happy to talk to you about it. Or if you see me around.